Those of you that have Ozzy know that he's an incredible professor. Ozzy's won lots and lots of teaching awards. He's recognized as one of the best teachers in the department. He's a member of the UT Academy of Distinguished Teachers, which is a really big feather in the cap of any teacher. And he's just great for our program, and you'll understand that when you hear him speak today. So I'll just turn it over to Ozzy. Ozzy Aywak.
Thanks, Rich, for the nice introduction. Can you guys hear me? Are the speakers working okay? Adjust. How about now? Just by way of introduction, I joined the Civil Engineering Department. It was called the Civil Engineering Department back then, about 15 years ago. And these alumni luncheons did exist at that point in time, and I thought that was something that the older professors in the department did. And here I am talking to our alumni today, and I'm not sure how I feel about that, but it's great to be here. As one ages, and I do, one thinks about, there is the technical details of a great many research projects, the textbooks that we teach from to our students. But you also sort of step back and take a look at where are we and where are we headed as the structural engineering profession in the country and the world. And within the framework of today's half hour to maybe 40 minutes worth of the talk, I will share some of my thoughts in that regard with you. Just to set up the stage and to provide context, obviously the world population is growing. The figures that you see here comes from a very nice United Nations report. In 2000, we were 6 billion people were populating the Earth. In 2050, we're scheduled to be about 9 billion people or so. Currently, as it stands, we're past the 7 billion people mark. And on the right-hand side, you see how much we impose on resources. In 2000, that was 47 billion ton worth of resource consumption, and that's all of it, minerals, ores, biomasses, and so on. And that is predicted to about triple within this 50-year time frame. So you take a look at a population increase of about 50% and a resource consumption about a factor of 3. You may be asking yourself the question, well, that math doesn't figure, and that reason can be greatly attributed to the fact that we have a lot of developing nations, and those nations are up and coming, and as they do, we continue to measure economic prosperity with resource consumption, and therein lies the problem. And United Nations has this one publication on decoupling the economic growth from resource consumption. Very, very nice reading. The challenge of the 21st century within that context is to do more with less, because unless we do more with less, we're not going to go back here and have a significant impact on this figure, right? Each day in our workplaces, we're getting memos and we're reading up what the upper management thinks about what is the next thing that we need to do without any significant increase in resources. That's perhaps a good personal example to each one of us, but I will dig into that topic considerably within the framework of this talk. I will let you read the words. The quotation here comes from that report that I was talking about. What's important here is that I'll just say the urgent rethink that we need to go through, and the investment that is required in technology, finance, and social innovation. Obviously, as engineers and as structural engineers, technology is the portion that relates to what we do on a day-to-day basis. So within that context, let me just start my conversation on structural engineering and where we are and where we're headed, in my view. For the purposes of existing infrastructure, a great majority of us is focused on maximizing service lives. That is really enhancing our understanding of the loads and resistances and understanding the aging effects. because we have a largely built infrastructure out there. That's the transportation infrastructure, that's the energy infrastructure, that's all of it. So what to repair, when to repair, how significant the repair job should be, and what to demolish and build from ground up is what we need to decide on. As for the new construction, we have to do a better job in using resources efficiently if we would like to impose on the natural resource consumption a little less than we have in the past. That implies optimizing conservatism, and I will give an example of that. And that implies reducing some of the design expressions that we have in the codes to the bare minimums without losing the essence of those equations, because that actually makes us better engineers. And ultimately, we're in the business of improving the quality and consistency of the constructed facilities. Obviously, that goes without saying. So the first example that I will use is on the optimizing conservatism side, and this is the research that took place at the Ferguson Structural Engineering Lab over the span of about 12 years. So we started someplace in 2002, and our research programs, 4 major TxDOT research projects spanned over 12 years. We started out with a significant literature review of figuring out what's happening in the world in terms of strut and tie. Proceeded to testing some of the largest beams ever tested in the history of shear research. The beam that you see in the setup here is about 75 inches deep, and by far the tallest ever tested in short shear spans available in the literature. Came up with some design expressions, and after that we looked into the design implications of that, and finally ran another research project in which we worked on a more complex loading scenario to see if our conclusions were going to stand up. Long story short, on the left-hand side you have the performance of what we have in the code as it stands today. So that's our bridge design code, AASHTO, and you see the statistics given at the bottom. The bottom line is that we have a fair amount of scatter in the data. We have a coefficient of variation of about 0.69. We don't necessarily have a safety-related issue that requires immediate attention. But if we wanted to impose on resources less, and if we would like to optimize conservatism, we can perhaps do a better job with the design expressions. So this is coming out of our recommendations to AASHTO, actually. What that does is it reduces the scatter, and the coefficient of variation ends up being, as an example, 0.28 in relation to 0.69. So there's a bit of a good news here. Earlier this year, I gave a talk at Saratoga Springs at the SCOBS meeting of AASHTO, and as it turns out, effective January 1st of 2016, our recommendations are making their way into the code. So 12 years worth of research, dozens and dozens of graduate students, many thousands of man-hours later, we're having an impact on a national design code. And in the next code cycle, the strut and tie design provisions that you will see in the code will be the ones that were developed at Ferguson Laboratory. Let's talk about minimizing complexity. And there was a decided move on my part here. I'm sure you can clearly read the equations that are given on the bottom right corner. This is going to feed into the professional training credits, education credits that you intend to claim after this talk. There will be an exam after my talk, and we will ask about this equation. Obviously, the intent is not that. The intent is just to tell you that what we have in the code is so complex that for a typical pre-stressed concrete beam that we have down the street here supporting a bridge deck, it requires 600 mathematical equations for somebody to calculate pre-stressing losses. That's a little much. And in particular, if you take a look at some of these data points here that are sitting on the unconservative side, you realize that you're carrying out 600 mathematical operations, which you really can't. It implies you're buying a piece of software that you're using in your design world because it's too complex. And in the end, you still have some data points that are sitting on the unsafe side. What you see here is our recommendation for the bridge code again. And 600 mathematical equations are reduced down to 60. Number of unconservative estimations have been eliminated. virtually down to 0. There is a slight improvement on the coefficient of variation from 0.24 is what I had on the previous slide to 0.2, but that's not the point. The biggest point here is 600 versus 60, and the second point being that we can eliminate some of the unconservative estimations. So this is along the lines of minimizing complexity, and just as an example. So what's changing, right? Going to high school and undergraduate school, and then to graduate school, some of us served in some of the competitions that take place in local high schools. There, the basic definition of structural efficiency that we describe to up-and-coming engineers is that we would like to maximize the strength of the structure for a given weight. So that way we're utilizing the materials in a most efficient manner. But in the 21st century, the challenge that we're fixing is that that definition is no longer satisfactory. We have to find ways in which we can address issues of durability, functionality. A roadway that basically looks like that is certainly not acceptable, and you can only widen the road so much, and so you're going to get into issues. You hear everybody talk about sustainability, so all those thoughts need to figure themselves into our basic definition of structural efficiency. I'm going to give an example of a recent research project that I got involved with. That's on the nuclear power side. And there I am working with expert chemical engineers, nuclear engineers, mechanical engineers. I serve the role of a structural engineering professor, I will say, who's running some structural tests at Ferguson Lab. We do have materials experts, and just from a scale standpoint, all the way from a materials issue up to the structural level, and all the way from civil structural type issues to all other aspects, environmental impact, the nuclear aspects of it on the demands imposed on the structure. Multidisciplinary team ends up being necessary. These days, we hear a lot of references made to interdisciplinary efforts and multi-scale efforts. I'll give you my definition of it because I have seen the terms actually, I'll use the term be abused in the sense that there are some individuals out there who would then claim that, well, I'm a great materials engineer, I'm a great structural engineer, I understand from chemistry, and I got all of this figured out. My way of looking at it is very simple. I'm a structural concrete person, and I do have a certain amount of depth in that area, and I can put that on the table. And by definition, I have to work with colleagues who have significant depths in all other aspects of those problems to where we can have a significant impact. Keeping up with the times. So the 20th century picture, Second World War ends, we come back to our country, and infrastructure expansion is taking place. At that point in time, the code priority is go from a place where we don't have a design code to have a design code that's on the safe side, and therefore the emphasis ends up being establishing the fundamental behavior, keep things as simple as possible, come up with lower bound expressions that we can use in our designs. Obviously, the approach that we took ended up imposing on resources in a significant sort of way. The 21st century version that is presented at the bottom left figure, that's a picture that was taken in Houston. There's a lot of maintenance type work. That particular bridge band is suffering from ASR, and Texas Department of Transportation is trying to figure out what to do with that particular band cap, because anytime we see alkali silica reaction out there, or delayed ettringite formation, or some other materials related problem that may have structural implications, we can't be in the business of tear it down and build it from ground up. Therefore, we are mindful of conservation, and what that does is it requires us to rethink what we're doing within the framework of design codes and refine the techniques that we have been using. I'll say first priority, and the places in which you will see the greatest impact will be the critical infrastructure. So picture on the left is the South Texas project. Basically, you're looking at a 2-unit nuclear power plant here. Each one of those units, if you wanted to build it today from ground up, you're talking about an $8 to $10 billion worth of investment. So it's not a small investment. Obviously, nuclear safety is important, public safety is important, and passing judgment on how many years we keep these facilities open, do they continue to be safe, and when to pull the plug on them is a substantial responsibility. Hoover Dam and bypasses shown on the bottom right corner. Every percentage of additional accuracy you can achieve may or may not mean much for the new construction of a typical overpass. It may impose on the materials by utilizing 10 or 20 more stirrups or something. But if you're going to pass judgment, once again, on a multi-billion-dollar investment, every bit of accuracy and better insights into what may be at play ends up being important. Another example for the potential value of innovation is the construction of 2 units that are underway at the plant Vogel in Georgia. So what you see here is the nuclear island construction. It's an old picture, certainly from the time that this picture was taken to date. Construction has continued. You see the 2 old units here, cooling towers on the top right corner. Units 1 and 2 were completed in 1989. And we're talking about a $9 billion worth of investment to produce right about 2,400 megawatts. And the units that are under construction is about to produce a comparable amount of electricity. Well, how does that compare to some of the green sources? Let's talk about wind power. The largest wind turbine that you're going to find out there is about 8 megawatts. And they work at an efficiency of about 20% on average. So 0.2 times 8 is equal to 1.6 megawatts, and you can figure out how many windmills you're going to need to basically produce that level of electricity. And the final example I will use is that research project and the case study that I would like to cover here. In the Northeast, one of the plants in, I think, 2010 came to the conclusion that they have ASR in 5 of their safety-related structures. And that kind of material degradation certainly raised some concern in the plant engineers and some of the local residents, and certainly the NRC. And the resolution of it is requiring a large team of dozens and dozens of engineers, and at the University of Texas, quite a few of us and our students to contribute to that effort. In a nutshell, ASR is nothing more than having a high alkali pore solution and a reactive aggregate, and a chemical reaction that takes place at that level produces an expansive gel, and when that gel absorbs water, it does cause cracking, and when that cracking is in place, basically you may have a structure or a structural component that may look like what's shown on the right-hand side. Just for, once again, reference and for the record, the picture that you see here was not taken at the nuclear power plant. It's one of our beams at the University of Texas, just to clear the air in that regard. Right? Once again, it's a beam picture that was taken at Ferguson Lab in 2011 as part of a textile project. But this is what ASR is going to look like under a microscope. So you see a dark rim. That's the ASR gel. You can see that the cracking is basically emanating through the concrete. At the structural level, macro level, the view is going to be a little different. So the typical structural design approach that we take, it doesn't matter what we design, we basically have a model and we feed mechanical properties into the model. And as the old Western movie goes, we decide if the situation is good, bad, or ugly, right? And we can design and detail this particular structure to where it can withstand the design effects, right, or the load effects that we have in the original design. By the time we have ASR in our hands, what happens is that some of these properties that are listed here do change, and the issue is what do you do about it? So I'm going to show you very quickly some materials data that we picked up from literature, and in the plots that I will show you, basically the data is coming from cases in which plain concrete elements were tested. So this is not reinforced concrete. So it's just at the materials level, plain concrete elements. And I'm going to show the guidelines of Structural Engineering Institute at Britain as to what their recommendations in that regard are. Looking at the compressive strength, as the ASR-related expansions grow, what happens is that the compressive strength basically drops down. At large levels of ASR-related expansions, basically we're talking about losing 40% of the compressive strength. And very quickly looking at the tensile strength, at large expansion levels, we're talking about losing 60% of the original tensile strength. Some of you, well, all of you are structural engineers, and all of you have taken, well, most of you are structural engineers, and we have Rich in the audience. So we don't necessarily use tensile strength of concrete in our structural design equations. With one exception, the nuclear containment vessel is designed per ASME, the mechanical engineer's design guidelines, and there the tensile strength of concrete makes more appearances than you would find in some other documents. Looking at the elastic modulus, once again, as the ASR damage sort of sets in, you may be losing 2/3 of the initial modulus. Coming back to this example and picking up our initial material mechanical properties and introducing an impact on the mechanical properties, you reduce the compressive strength of concrete by about 40%. The situation is going to be past bad. There is no way that I can imagine that you can make your design work. Once again, tensile strength is going to have a huge impact on the containment calculations, and certainly that's not going to figure. Elastic modulus is a little more murky, because envision a case in which we lose all of the stiffness, right? Modulus goes down to 0. The ground could be moving in a seismic event, and the structure stays where it is, so it's unable to attract forces. So depending on what you're talking about, modulus loss may be good or bad or perhaps ugly in some cases. The reality of the matter is, reading through the literature and looking at some of the British research, we're being told that structural context is very important, and one must reconcile the confinement offered by the rebar gauges that we may have in place, rather than get carried away with the behavior of plain concrete. I will share with you some of the results from a recent research project at Ferguson Lab. This is a research project that we have done for Texas Department of Transportation in an effort to establish the structural impact of ASR. Looking at the end of this beam R3 that was manufactured in 2007, so here's a crack width of about 5/8 of an inch, just for the purposes of scale. Basically what that implies is that you can have this iPhone and you can actually stick it into that crack. The reason the cracks can be so large is in the end face of the beam, we don't have a rebar mat that's crossing those cracks, and the cracks are able to grow freely. As opposed to the side face of the beam, where the situation is a little different, we can take a look at the cross-section of that reinforced concrete beam, take a horizontal cut, and work on the mechanics and figure out the effects of confinement, but that's not the purpose of today's talk. Focusing on the side face, you can barely make that. We have micro cracks or hairline cracks scattered all over here, but you take a look at the end face of the beam, you can immediately see the role of the rebar mat that may be present in that beam. Let's take a look at the structural response. Fairly interesting structural response here. Top right, we have the non-reactive beam, so that's the control beam, and we have the beam that has suffered a significant amount of ASR damage, and that would be about 0.6% worth of expansion in the vertical direction. So the stirrups have been pushed to the yield point and past that by a factor of 3. So that's a fairly significant level of expansion. So in the linear elastic range, the impact of ASR is equal to 0. Past the cracking point, it looks like the stiffness is a little better than the control specimen, and the strength appears to be significantly better. I can tell you that the graphs have not been mislabeled. You're looking at real data, and what this leads us to say, and we have said it in our TxDOT report, is that basically due to a chemical degradation mechanism called ASR and its impact on the shear strength of reinforced concrete, there is no impact. Certainly we're not going to say that ASR is great. Try to build it in your structures and it improves capacity. In the end, we're responsible structural engineers, but I think it's fair to say that the impact is fairly negligible. In a nutshell, when the compressive strength of concrete drops from 7 KSI to 4.5 to 4.2 KSI, shear strength seems to be having a different trend, and you can see the code calculations level here. Certainly it poses about 0 thread. Exact same information given in a tabular form. You can see that the test shear basically increases with increasing levels of ASR expansion as the compressive strength is on a decline. So the integrated perspective is that you can't and you should not just pick up the material test data, neglect the fact that the material is confined by its surroundings. That's the structural boundaries and rebar cage and all the rest of it, and come to the incredibly conservative and potentially bad conclusion that ASR has a significant impact on the structural response. Instead, the role of confinement has to be understood, and assessment of existing structures should focus on unreinforced, poorly confined cases, right? But great news until you read some more, and these pictures are coming from Japan. What you see here is a rebar that's coming in the vertical direction, so that's the other portion of that stirrup, and basically there is 30 reported cases in which rebar fracture took place in Japan. It's a combination of a lot of different issues that figure into it, and corrosion certainly is a part of it. And there are some differences in their materials and ours, mandrel diameters that they use in bending the bars. So there are good technical reasons why there has been cases of rebar fracture, and a lot of them reported in Japan and non-reported in the United States to date, according to my knowledge anyways. So looking at the conclusion of Miyagawa, I will just say it's a very simple conclusion. Japanese researchers concluded that you don't have a problem until you do. It's absolutely not a problem. And then when and if rebar fractures, you go from not having a problem one day to having a lot of problem the day after that. So it's a bit of a tricky problem that requires continuous monitoring and significant insights into it. In the nuclear power plant example that I was giving, there was a lot of structural walls with ASR damage. Certainly in the vertical direction, as ASR affected concrete tries to expand, we have rebar that's restraining that expansion. The same argument is going to apply in the horizontal direction, and expansion in that direction is restrained. But then there is the through the thickness direction, and as concrete tries to expand out of plane, there is nothing there to restrain it. It is for that reason that our current efforts at Ferguson Laboratory are focused on basically looking at the out-of-plane behavior of these structural walls. So a group of us at Ferguson Lab with our students are working with engineers on the other side, on the nuclear engineering side and chemical engineering side and so on, and we're trying to pull together our areas of expertise to come up with a solution that is sound, and we are about to actually share that solution with the owners of the plant alongside of NRC within the next year or so. And certainly the integration of the durability expertise into our group has also played a significant role. Let me deliver you some good news. This is my second to last slide. And with that, I will share some sort of higher goals that we have. In the middle, we have a black box. So for the purposes of this talk, let's call that the computer program. We have looked at data at the materials level that says with ASR degradation, mechanical properties basically head in the wrong direction, right? They go from being good and sound to much less than so. Structural testing conducted at Ferguson Lab to date and elsewhere, all over the world, basically show little to no effect, structural impact of ASR-related expansions. Certainly, expansion information and ASTM tests and so on are in the picture. And you start looking at a real structure, for ASR reaction to take place, we need three basic elements, right? We need the reactive aggregate, we need a high alkali pore solution, and we need the presence of moisture as well, right? So if you take a look at an existing structure, what happens is that portions of that structure may be exposed to elements, and therefore moisture may be present. Other parts are protected, therefore moisture isn't there. So all of that information and the local conditions need to be fed into that mechanics-based model. And degradation certainly has to be modeled. So ranging from what happens at the materials level and what happens at the structural testing level to in situ conditions, my hope is that within about 5 to 10 years time frame, we will have this problem bottled up to where we can have comprehensive computational assessments. Our current higher goal of coming up with a solution that can be offered to the world. But with that said, that's where all these efforts are headed towards. So what does this mean? This particular plant, located in the northeast United States, produces power for 1.4 million homes. You're talking about 2 to 3 people per house, so that's about 3 to 4 million American citizens drawing electricity from this plant. And what we're trying to do is we're trying to work within our multidisciplinary team to offer a solution here. This simple statement that why don't you shut down the plant and build a new one, well, it's only a question of money. $10 billion later, one can do that, but that has an impact on power rates and so on and so forth. Our approach is that when and if there is a structural problem that actually that's a cause for concern, we should do something about it. With that, I will stop my talk here and entertain some questions.
You answered them all, Oz.
I answered them all. That just can't be. Yes?
Is there something about nuclear power plants that drives
Alkali silica reaction? No, if you take a look at, for example, the city of Houston and talking to sponsors, colleagues, engineers from Texas Department of Transportation, depending on who you talk to, the ASR problem in Houston is a multi-billion-dollar problem. It exists in a great many bridges, and they're basically managing the problem by monitoring plans and so on and so forth. It's got nothing to do with typical nuclear power plant, and these are all the things I had to learn over the past 5 years or so. There's about 18 or so buildings, of which one building is the containment building. Outside of that building is the containment enclosure building, providing an umbrella for the containment, therefore keeping it dry for the most part. There is the control buildings and tunnels and so on and so forth, right? Fuel storage buildings, the list goes on. So a great majority of a nuclear power plant, as I understand it, has got nothing to do with radiation exposure or anything like that. Now, irradiation and what that does to mechanical properties of concrete has been studied, is being studied by quite a few people around the country, but ASR has got nothing to do with the nuclear reaction. It is just the use of high alkali cement, right? Or it may be that poor solution for one reason or another. It could be the external sources that are driving this in are rich in alkalis. You need to have a reactive aggregate, either coarse or fine aggregate that may be reactive. And you need to have the presence of moisture, so that's maybe north of 70 or 80% relative humidity to drive this reaction. It does exist in dams, foundations of power lines and so on, so those towers, there is many examples of it. It just, this particular is the first reported case of ASR in a U.S. nuclear power plant. And to put that into context, we have about 99 or 100 or something like this right now, operating units in the country.
So geographically, you talk about 80% humidity, coastlines more prevalent to have it versus out in the middle of the desert?
Well, so that's an excellent observation. In the simplest possible terms, the answer is yes, but not quite, because what happens is that depending on what type of concrete it is and how porous it is, from the get-go we have a substantial level of moisture in the fresh concrete mix. And I have worked on, for example, high-performance, high-strength concrete, and you test a column that's right around 15 or 16 KSI concrete some 3 or 4 months after its construction, and after the spooling of the cover concrete, if you were to lay your hand on the structural core, it's basically moist. The concrete is so dense that it never dries out. So there is an inherent internal level of moisture that's in there that can drive this reaction. And there has been cases in which fairly dry areas, including I think Arizona, where we have seen examples of ASR. So it doesn't fit the moist environment picture. It just fits the fact that, you know, from the get-go we had some moisture in concrete.
Several years ago, I saw the results of a study by an ASCE committee on this astounding amount of money it would take to recondition our infrastructure, I presume, bridges and so forth. And it was just billions and billions of dollars. And I'm wondering if there's any sort of information available on what kind of progress is being made toward that here in the U.S.
So to give you solid facts on that question, I'm going to have to say I don't know. But with that said, let me give you my insights as to what I think is happening, right? If you take a look at, for example, the ACI building code for new construction, we have pulled it together. A great majority of it existed in the 1960s, and we have been improving it since, right? But for the purposes of evaluating a bridge that's showing some cracking, spalling, corrosion, whatever, carbonation, whatever the case can be, do we have a nationally accepted, commonly utilized, concise guideline, one-stop shop that we can use to evaluate that structure? The honest answer to that is I don't believe we do. We have documents that we can use for different applications and different degradation mechanisms and so on. So with I don't know, north of $1 trillion worth of investment on, say, transportation infrastructure, I don't think we can say that anytime we see a durability type issue, just tear it down and build it up. There is going to be a lot of emphasis placed on that, even here in Texas, where we have a lot of new bridges moving forward. How is it being handled is a great function of which state you're in. State Department of Transportations have a substantial amount of autonomy within themselves to make these decisions. Years ago, I was contacted by, for example, Oregon DOT for some shear cracking issues they were having in a series of bridges, and how they handled that problem is different than how such a problem would be handled in Texas. It doesn't make one solution or the other better or worse. It's just there's different ways of approaching such problems. And it's a huge issue. And what that does is it renders civil engineering, renders our profession ever more important. And quite frankly, having to pass judgment on existing structure that has a lot of unknowns associated with it is a greater level of engineering, and hopefully that may even have an impact on some of the work that we do in the future.
How is the NRC responding to your, the information you're providing, being it takes about 10 to 15 years to get licensed to run a new plant?
So,
I know a little bit about the South Texas project. I know some of the designs were in the mid-70s that came online in '88. So it's kind of time
frame. Here's my understanding of the NRC perception. I can't speak for the NRC certainly, but this plant has a existing license that expires in 2030, and they're in the process of seeking a license extension. And so where the license extension side is something I will not talk about, but even today they're licensed to operate until 2030, provided that the plant is safe to operate. So how the NRC is responding to this involves, my exposure of it is we do have NRC inspectors come to our lab on a routine basis. I cannot even tell, dozens of times, multiple people basically scrutinizing anything and everything that ranges from where the material was procured. For example, to make the concrete that we're utilizing in these specimens, we have trucked aggregates from that region of the United States We went to the cement source that was used in constructing that plant, and the list goes on. From procurement of the materials to make the beams, to the details with which the beams were fabricated, to the test results and so on. It's a real-time exchange back and forth, which was a learning experience for me, because you work on a research project for TxDOT or NSF or some other sponsor. You say, here's the dollar amount and here's the number of years, and those are the objectives you would like to achieve, and we will send you a report when we get done, right? You may have project meetings, but you're basically sitting there doing the research for multiple years. On an issue like this, it's real-time information dissemination. NRC has unfettered access to any and all of information at Ferguson Lab. We have an engineering company that's basically picking up the results from us and utilizing it. Actually, we have more than one. We have two. They're utilizing the information generated at Ferguson Lab to basically pass judgment on the plant, and that real-time feeds into NRC, and they take a look at it. In official terms or bookkeeping terms, I think the plant in this regard is classified as operable but degraded, because there is an open issue on what the impact of this chemical degradation mechanism is. And that needs to be closed at some time, but I'm not quite familiar with all of the NRC ins and outs, to be honest with you.
So what it's sounding like is you're really worried about looking at the materials used, because though you're talking it's not necessarily an environmental impact, concrete loves to soak up moisture. It needs moisture. So if it's too dry to start with, it's going to try to find that moisture.
Sure.
Which, if you're around a high, basically a high salt, high sodium, it's going to absorb the sodium with that water.
Sure.
So, have we noticed a whole lot of issues with our structures so far? I mean, the alkali silicon reaction takes some time.
Yeah. So there is two pieces to that question, I think. I can give you a past experience from a field testing project, again for TxDOT, of drill shaft foundations that are, seem to recall, maybe 5 foot in diameter that we have tested in, right at Beltway 8 and 59 in Houston. So the top portions, exposed portions of those foundations actually look like they have fairly large cracks, but we excavated around the drill shaft to where we can actually observe the concrete surface as we test it. The very first observation I had is the portion of the drill shaft that's below grade, right, which has been exposed to almost constant supply of moisture. We're talking about Houston. The cracking pattern that we saw there, we couldn't see a cracking pattern, right, because of the fact that it was basically moist at all times. The portion that was wetting and drying all the time on the top side and exposed to elements, the cracks appear different. So that is how the impact of or presence of moisture may impact the cracking pattern. From the standpoint, there was a second piece, and my mind is wandering here. Did I address most of it, or? I just remember. The second piece is, for the work that we're doing for the nuclear power plant, so the issue is you can go back and try to the extent possible, generate the exact same concrete. Well, the exact same concrete may give you the exact same time frame for the development of ASR. So for this plant, it took about 20 years to get to the level that they're at. So we have now 3 to 4 years to take the specimens from no ASR damage to the plant level ASR damage, 5 to 10 times plant level ASR damage, to where judgment can be passed on. Is it okay right now? Will it be okay next year? And so on, right? And rightfully so. So what that did is, and the source of ASR in that particular case, or the reactive aggregate, ends up being the coarse aggregate. So we actually picked up 50% of our coarse aggregate from the exact same or a very similar quarry up northeast. The other 50% comes from New Mexico. Similar mineralogy, but there are some differences, and those differences actually drive a chemical reaction that's much faster. So it's striking a balance between maintaining the key parameters to where you're not losing the representativeness to the plant, yet it can't be exactly the same, because the exact same thing will give you the exact same time frame, and nobody has got that kind of time or patience to get those results, right? There is a lot at stake in terms of safety.
Are there materials tests being done now on aggregates and cement to try and come up with better guidance for what to use so you don't have the ASR problem?
Oh, yes. So what happened is that, and strangely, and as I understand it, the plant itself did run ASR reactivity tests in a whole slew of tests, and came to the conclusion that their aggregates were not reactive back before the time of construction of the plant. But the ASTM specs have improved in time. So if we go back and pick up the plant materials and run the same ASTM spec test back then, that version of it, it will show that it's basically well within the thresholds, and this is not exactly a reactive, this is not an aggregate that can be classified as reactive. The current version of the ASTM specs, with the revisions that took place over the years, will in fact pick up this aggregate as a slow reacting coarse aggregate. So in some way, they have done their reactivity testing, but what we knew back then is not what we know right now. And I think that all the research that has taken place on the materials side placed us in a much better shape. And yes, they do run those tests.
Did you uncover any surprises during the research, those of significance that surprised you?
Yes. So I mentioned that we're working on an out-of-plane behavior, or all issues related to out-of-plane behavior of those structural walls. But what is that? Well, that's the shear strength of a wall that does not have stirrups, right? That does not have shear reinforcement, is item one. Item two, you have dowels coming out of the foundation, and you have the steel coming from the structural wall, and you have the lap splices, right? And you see the cracking in the concrete, and you're looking at it, and concrete tensile ring that clamps this rebar to the other is what allows you to transfer the force from this one to that one as you put it in tension. If you introduce cracks on that tensile ring, will you be able to transfer the force? And I was sincerely concerned about that, right? And I was also sincerely concerned that ASR is basically going to grow in the direction of least restraint, right? That's through the thickness, and shear force is coming in that direction. I was not too sure where the test results were going to go. But I will tell you that we have completed maybe 50% of our testing, not a single test result that shows any structural degradation, be it on the shear side, on the rebar anchorage side. We're currently working on the mechanics of why such is the case, but the reality is we have not seen any degradation. If you asked me several years ago, could you see some degradation? I would say, well, the testing that we have done for TxDOT has always been in cases in which we have rebar in the X, Y, and Z directions. So there is some level of confinement always. And in this case, we're missing through the thickness reinforcement, and that may be bad news, right? So as it turned out, the results are coming the way they are, and that was a bit of a surprise to me. James.
Philosophical question, but so when we're talking about ASR, I guess your primary concern is trying to figure out more or less if we're able to get to the design life of whatever has been designed.
Yeah.
I guess if we're talking about trying to improve efficiency and the use of resources in the future, so I guess this is just one part of that question. It really is: can we design to the level that we think that we're designing to? And then on the other side, I guess we also have to address the question, are the design lives that we're picking out substantial or sufficient enough for trying to kind of mitigate this, knock it down, rebuild it sort of cycle of construction? I was wondering, can you speak to that a little bit in terms of how that might play with the research that you're doing? Like, what are your overall thoughts on how this plays into our pursuits of efficiency with what we're doing, taking a look at ASR particularly.
I can tell you that in the recent past, I mean, on the bridge side, there's always this talk about a 100-year bridge, right? Life expectancy of about 100 years. And some people even started talking about longer lifespans than that. There's a little bit of a humor in that, because those of us who are talking about a 100-year life expectancy, including myself, will not be here, so somebody can call us to task and say, well, you said 100 years, it was really 78, right? But coming back to the technical essence of your question, yeah, there is a lot of things that we're learning that should be translated into new construction to where greater service lives can be achieved. But that's much more than ASR, right? So there is all the chemical degradation mechanisms that we know that concrete can potentially suffer from, right? And we are in a position to do something about it. As I understand it, for example, let's use the example of El Paso. There is a new precast plant that's being built there for the purposes of providing bridge beams for a highway that's going to be, I can't remember the name of the highway, border highway or something along those lines. Lots and lots and lots of bridges, and you're not going to truck concrete pieces from central Texas to El Paso. So what you do is you come up with a plant right next to an aggregate source. Guess where our reactive sand is coming from? El Paso, right? So now, does TxDOT and structural engineering community and material science community, do they know that we have reactive sand in El Paso? Yes, they do. So the use of 25% fly ash or 25+% fly ash, and there is mitigating techniques that one can use to where reactivity of aggregates can be handled, and that's getting figured into the materials design, mixture design aspect of it. But once again, there is much more than that. Let's start with those of, well, I mean, everybody here is a graduate of our program, so let's talk about Austin. You're going north on I-35 and with the hopes of coming to Dallas, and you realize there's a flyover, beautiful bridge designed by a former Longhorn. Let's give him credit. Single lane, right, to get over to 183. As I understand it, from talks that I listened to in Washington, D.C. at TRB, that bridge was deficient from a traffic standpoint at the day that it opened, because it's just a single lane and it didn't cope with the volume, right? So then the logic that we may have is, do we need to scale our thinking, right? To say to this generation of taxpayers that, why don't we build a 16-lane highway? Well, because we don't have the money for it. So how can we scale our thinking to where tear it down and build a wider one is not something we do, but can we make it adaptable to where we can add lanes to it and ways in which we can tackle future growth? Yes, that may impose on the initial cost by 10 or 20%, but I'm willing to pay for that so my kids can utilize the bridges that we're building today and they can be widened. So that's the functionality end of it. So there is the material durability end of it. There is structural detailing end of it. If you're detailing your structure to where you're leaving, for example, on the matter of the nuclear power plant, if those walls had Z-direction reinforcement or through thickness reinforcement, research conducted to date is sufficient to answer those questions. So they would have been much further ahead of the game, right? But for the fact that they're missing that reinforcement, as is the case in any and all structural walls, or most of them, right, they're having to deal with this issue. So then the learning could be, if you can provide a minimum amount of reinforcement in structural walls that are going into multi-billion-dollar facilities, maybe that's an incredibly cheap insurance policy. So there are some learnings that can be translated and conveyed over to the profession, and that's just one of them. I'm being told I can only take one more question. So let's make that question count. I like talking, so.
Can I ask? Oh, I'm sorry. I was going to ask, but if nobody else had any. Go ahead. The non-structural engineering.
We'll make it 2 questions. He's our department chair, decides on my pay raise, so.
We've been pre-stressing bridge girders for about 65 years, I guess. Are you saying deterioration and pre-stressing and pre-stress?
Well,
Most
pre-stressed concrete bridges, Precast Pre-Stressed Concrete Institute and American Segmental Bridge Association have participated in studies that I have listened to presentations in the recent past. From a durability standpoint, you can't do much better than pre-stressed concrete. Do we get into issues? Yeah, there are some issues that we get into. There has been pre-stressed concrete bridges that got replaced for the fact that materials degraded to air. It just, structurally it may be okay, but functionally, you don't want to be in a situation where large chunks of concrete are falling on the oncoming traffic. So that's not a structural issue, but that's a real safety issue. So there comes a point in time some of these decisions are being made, but pre-stressed concrete bridges are very, very durable bridges, and that doesn't mean to say they don't get into some retrofit issues every now and then, but by and large, from a cost efficiency and durability standpoint, you can't do much better than that. Talking to a fabricator from Victoria, Texas, who built the first set of beams that went into the first pre-stressed concrete bridge in Texas. That bridge is alive and well. It's got some cracks in it due to applied loads and so on, but it's in service and it's doing well, so it's a wonderful material. Rich?
So I was going to ask, it seems like there's a changing nature of fly ash in the United States.
Yes.
How does that affect DCR? I mean, we're burning different coals now than we were 10 years ago, and that produces a completely different type of fly ash, right?
It is. It is an ever-evolving set of constraints. Not only that, the cement chemistry is also changing or has changed over the past. So it just highlights the importance of, I'll just say, materials research in covering new materials that are up and coming, and what works, what doesn't work, do we need to tweak percentages and so on, because if we really and truly would like to be proactive, and we can't equate the cement that we're importing from, I'll just say, it doesn't matter which country it is, and some of the local sources. Even if you take a look at the local sources in the process of procuring cement for our research program, there's a huge variation that you see in cement chemistry coming out of one plant versus the other plant, and every single one of them do meet the spec. So there is a lot of value in getting your feet wet and doing some testing, particularly for really, really expensive structures that we're putting out there. Well, additional questions, maybe I'll take them over the, is there a coffee break or?
Yeah, we could, if you'd like to stick around for a few minutes and talk to Ozzy and talk amongst yourselves, that's great. But I want to thank Ozzy for an incredible presentation, even structural engineer.